Hello, this is Mr. Mac. Now, I want to talk to you about polynomial functions, and there's kind of a lot of stuff, so it's going to be one thing after another for a little while. So first of all, if we have a polynomial in one variable, remember, polynomial is what you tell a fat parrot. Not really, but anyway, if you have a polynomial in one variable, then you'll perhaps have a number of terms like 5x to the fourth plus 2x to the fifth minus 3x squared plus 17. We might call this f of x, for example, a polynomial function. Now, this is a polynomial in one variable because all the variables are x's. And there's a number of things that we want to take a look at with this. First of all, we want to define the leading term. Now, the leading term is not leading at the moment. The way I've written this, the leading term is actually the second term. The leading term will be the term where the variable has the highest exponent. And when we write polynomials, we like them written in order of decreasing power. So we would think of this really as f of x is equal to 2x to the fifth plus 5x to the fourth minus 3x squared plus 17. That would be in order of decreasing power. This term has a degree of 5, this term has a degree of 4, this term has a degree of 2, and this term has a degree of 0, because there is really a phantom x to the 0. Remember, anything to the 0 power is 1. 17 times 1 is 17. But what we're interested in thinking about at the moment is the leading coefficient, or the leading term. Now, the leading term has a leading coefficient. In this case, the leading coefficient is 2. And the leading term's exponent, if it's a polynomial in one variable, is the degree of that polynomial. In this case, the degree is 5. Now, it's going to become important to us to be able to identify the degree of a polynomial in one variable, and sometimes the leading coefficient is going to help us also in finding out other things about the polynomial function. Now, graphs of polynomial functions, in other words, if you have a polynomial function, the graphs are continuous and smooth. Now, continuous is a mathematician's term to say you could put your pencil down on the paper and draw the curve and not pick it up off the paper till you were finished. Well, actually, there'd be more over here, but the idea is any part of the curve you choose to draw will be connected. You can draw your pencil through it rather than having to pick up your pencil and put it back down again to draw another part of it. And smooth means that they curve, they go up and down, but they don't have sharp ends in them. You won't see something like this. This is not a polynomial function graph. The graphs of polynomial functions are continuous and smooth. Okay, now, if you have a polynomial function that just has one term, for example, if g of x is equal to 5x to the 7th, we would call this a power function as well. It's still a polynomial function, but we would call it a power function as well. The next thing that we want to get into is functional notation with polynomials and using variables as inputs. So let's start out with something simple. Let's let f of x be 2x squared minus 3x plus 7. Now, we might ask, for example, what is f of 5? What that means is put 5 in for x every place you see x in the rule for the polynomial. That would be 2 times 5 squared minus 3 times 5 plus 7. Now, remember, order of operations, you do exponentiation first. So 5 squared is 25 times 2 is 50 minus 15 plus 7. Well, 50 minus 15 is 35. 35 plus 7 is 42. So f of 5 would be 42. Now, I'll bet none of you watching this video are really surprised by that. You're saying, Mr. Mack, I knew how to do that already. Well, of course you did. But now, what we're going to do is we're going to take this a step farther and say, what if we asked you for f of r? Well, r is now the input, so we put r in where we see x, and we would get 2r squared minus 3r plus 7. No problem, right? You say, no problem, just put r where x is. Yes. Well, how about f of 2q? Now that would be 2 times 2q quantity squared minus 3 times 2q plus 7. And this would require some simplification. Remember, you do exponentiation first. So 2q quantity squared is 4q squared. And 4q squared times 2 would be 8q squared minus 6q plus 7. Okay. Once again, not too bad. Wait for it. Here it comes. What if we were to ask for something really strange, like f of 3c minus 1? Now what we're doing is we're putting this whole binomial in for x every place we see it. So that becomes 2 times the quantity 3c minus 1 squared minus 3 times the quantity 3c minus 1 plus 7. Once again, some simplification is required here. When you're squaring 3c minus 1, you multiply 3c minus 1 times 3c minus 1. Now there is a quick pattern to use, and I'm just going to use that now. If you want to, you can go ahead and follow that out, but I have shown you the pattern, and I'm going to use it. So we have 2 times the first term squared minus 2 times the first, or plus 2 times the first term times the second term, which is minus 6c plus 1. And now we have minus 9c plus 3 plus 7. So this becomes 18c squared minus 12c plus 2 minus 9c plus 3 plus 7. Now we'll combine like terms. There's only one c squared term, 18c squared. Now minus 12c minus 9c becomes minus 21c plus 2 plus 3 plus 7 becomes plus 12. So the answer would end up being 18c squared minus 21c plus 12. You'll get a chance to practice that sum in the exercises that you're doing, so I'll leave that at that particular point. Now, we are attempting to make mature mathematicians out of you, so we would expect of mature mathematicians that they know what the graphs of functions like a constant function. If f of x is equal to some constant, the graph would be a horizontal line going through 0c on the y-axis. If you have a linear function, f of x equals mx plus b, that would be a line, and it would have a slope of m, and it would go through 0b on the y-axis. Now, for a quadratic function, f of x equals x squared plus ax squared plus bx plus c. The graph of that one's going to be a parabola. Notice, horizontal line for a constant. Up 1 degree, we have a slanted line. Up another degree, we have a curve. Now, f of x is, if f of x is a cubic function, f of x equals ax cubed plus bx squared plus cx plus d, the graph is going to have 2 turning points. Now I've drawn it so that it goes through the origin here, but that's not really the way it always happens. So let's just make this, let's just say there we go. Okay, so there's the graph of a cubic function. Now, we'll be talking about end behavior. They're not always going to be down on the left and up on the right if they're cubic functions, but we'll get to that. Now, and by the way, this is a cubic function because the degree is 3. Now, if f of x is a quartic function, that's degree 4, then our graph is going to go down and up and down and back up. Notice in the cubic function we had 2 turning points. It was going up, it turned and went down, and then it would turn back up. That's 1 less than the degree. In a quartic function we have 1, 2, 3 turning points. That's 1 less than the degree. Now in a quintic function, anybody care to guess how many turning points? A quintic function, if f of x is a quintic function, Q-U-I-N-T-I-C, that's degree 5, we're going to have 4 turning points. So we would maybe go up and then come down and go back up and come down again and up one more time. There's 1, 2, 3, 4 turning points in a quintic function. All right, now this brings us to the concept of end behavior. Let's go back and look at the quadratic function, degree 2. Now we know the graph of a quadratic function is a parabola. Now it might go like this, or it might go like that. But it's either going to open upward or it's going to open downward. Now, if the parabola opens upward, then as x goes farther to the right, f of x is eventually going to take off towards the skies with nothing to stop it, with no bound. Now, the way we would describe this behavior is we would write as x increases without bounds, f of x also increases without bounds. Now notice what I wrote was as x approaches infinity, f of x approaches infinity, but what I said was x increases without bounds and f of x increases without bounds. If you think of it that way, that should help. Now notice over here, as x gets more and more negative, f of x again is taking off to the skies with no boundary. So we would say as x decreases without bounds, notice what I'm writing is as x goes to negative infinity, f of x, still in this case, is going to go to positive infinity. So as x decreases without bounds, f of x increases without bounds. And this is end behavior. Now, the thing that makes this end behavior occur this way is the function is even degreed, and the leading coefficient is positive. Remember earlier I said the leading coefficient was going to be helping us out with these. So we're going to take a look at these and we're saying the function is an even degreed function and the leading coefficient is positive. Now, if our parabola opens down, what do we know about the leading coefficient? We know the leading coefficient is negative. Because, in other words, ax squared plus bx plus c, a is negative if the parabola opens down. Now notice again, as x increases, f of x decreases. So we would say to the right, the end behavior is as x, as, let's try this again, as x increases without bounds, f of x decreases without bounds. Okay, now pause the video here and try to write the end behavior for the other side of this parabola. Okay, we're back. Now, notice x is going this way, f of x is going this way. So we write as x decreases without bounds, negative infinity, f of x decreases without bounds as well. And that occurs when the leading coefficient is negative and the degree is even. So we'll get exactly the same behavior at the ends with a quartic function, that's fourth degree, a sixth degree function, an eighth degree function, a 42nd degree function, etc. Okay. Anytime the leading coefficient is positive and the degree is even, we get end behavior that goes up in both directions. Anytime the leading coefficient is negative and the degree is even, we get end behavior going down in both directions. Now, if we have an odd degree function, let's just start out with a cubic function. If f of x is a cubic function, not to be confused with cubic zirconium, the degree would be 3 for a cubic, that's odd. And let's say the leading coefficient is positive. Okay. Now, the graph will look something like this. So notice, as x goes to the right, f of x goes up, right? So we would say, as x increases without bounds, f of x increases without bounds. Notice on the other side, as x goes to negative infinity, f of x heads south. So we would say as x decreases without bounds, f of x also decreases without bounds. Now, think about this with me. If we were to multiply this function by -1 after the function were performed, what that would do is that would reflect this function over the x-axis. Let's see if I can do this. So what we would get, let's change the color on this. What color would you like? How about, oh, you've already used red. Okay, how about this? No, that's probably not really easy to see. How about brown? Yeah, there, we'll just do brown. Okay, so notice now, when we change the sign of the leading coefficient to be negative, our right-hand behavior, as x goes this way, f of x goes this way. That is, as x increases without bounds, f of x decreases without bounds. And over here, as x is going to the left, f of x is going up. So we would say as x decreases without bounds, f of x increases without bounds. And this is true for any odd degreed function. If the leading coefficient is positive, it's up to the right, down to the left. If the leading coefficient is negative and it's an odd degreed function, it's down to the right, up to the left. A couple of things to do here. You meditate a little bit, and I think you'll see or you'll realize that um, any polynomial function goes up to the right if the leading coefficient is positive. Any polynomial function does the same thing on the left and the right if the degree is even. Any polynomial function will do the opposite thing from the right and the left if the degree of the function is odd. There's all kinds of little connections that you can make there, and I challenge you to meditate on this sum and to make those connections. One more thing and we'll be done. Now, zeros of polynomial functions are places where the function crosses the x-axis. Now, if you have an even degreed function, it doesn't have to cross the x-axis. If left-hand behavior is up and right-hand behavior is up, then it could do something like this and never touch the x-axis. There would be no zeros. If you have, let's see, this is even. Now, if you do have, let me just get rid of this and do a maybe better job. If you do have an even degreed function, one of the things that's going to be true is we're going to talk about the idea that if you have real zeros, they kind of come in pairs. Now, I know when this is just touching, it looks like 1, but to mathematicians, we say that that's a root with multiplicity 2. In other words, it's the same root twice. And we think of that as 2 roots, okay, or 2 zeros. But here, notice we've got 2 zeros, and then we have 4 zeros, and then finally we have 6. 6. And then back to 4, because these 2 are now underneath, and then back to 2, and now we're at, we're still at 2 because this end over here is going to go up there, and this one's going to go up. So, but what we're talking about here is that if the degree of the function is even, we're expecting an even number of real zeros. It can be 0 or 2 or 4 or 6 up to the degree of the function itself. Notice I have 1, 2, 3, 4, 5 turning points in this one, and it's a possibility, that makes it 6th degree. There's a possibility really of 6 zeros. So one of the theorems that we're going to come up with before too long is that the total possible number of zeros for a polynomial function of degree n is n. And then notice that they kind of come and go in pairs. Now, if you have an odd degreed function, remember you have left and right hand behavior that's different. So now, if you look at this, notice I've actually drawn a cubic. There are 3 zeros, and here's 1. But since this keeps going down here to the left, there's no time where I can lift it up high enough it's not going to cross the x-axis. So an odd degreed function will always have to have at least 1 zero. An even degreed function might not have any, but an odd degreed function will have to have at least 1 zero. Now, with these pieces of information and the exercises, you should be able to do well on this part. So good luck on those exercises, and you really do need to do them. And we are done.